So, hello everyone. We're gonna hopefully get started. So thank you all for coming. Hopefully we learn a lot today. This kind of started out of, there was a discussion in Mike's group about, the cluster is new for a lot of people, and there's just this word getting tossed around, oh, run your jobs on Compute Canada. But if you're new and you're like, well, what is that? What is a scheduler? All these things. Where should I store my code? Things of this nature. So we got some very experienced people who are going to share their experiences and then hopefully, and their tips and their tricks, hopefully. And then move on to kind of a lab style where if you guys have specific questions about your workflow, problems you're running into, they'll be there to help. So to kick us off, we have Andy Patterson, and then we're going to go to Subo and Khurram. All right, thank you.
Yeah, it's funny, when we were first putting this thing together, it was supposed to be like, oh, we're just going to get a couple of students together, we'll have some like Q&A, and now we have all this. Things escalate really quickly. So for the most part, I'm going to keep a very informal tone. I'm probably going to start almost condescendingly low level. I assume most people here know what a computer is or have interacted with a computer in their life, but probably that's the base level assumption I will make. So treat this mostly as just agreeing on terminology. When we start talking about supercomputers or clusters, people throw around a whole bunch of different words that mean slightly different things. So we're just mostly going to agree on terminology here at the start. Oh, one bit of terminology that I will get wrong is it is now called the Digital Research Alliance, not Compute Canada. I'm going to continue calling it Compute Canada because I don't learn new things. Okay, so the plan for me for today is I will start with some terminology. We'll talk a bit about schedulers, specifically Slurm, the scheduler used by Compute Canada. We'll talk a little bit about storage systems, but more at an abstract level, and Khurram's going to go into some more specifics. We'll talk a bit about software and how you get software onto the Compute Canada cluster, how you actually run your software. And then I labeled this a few best practices, but then as I was typing up the slides, I realized it's mostly Andy's opinions. So maybe instead of calling my opinions best practices, a better title here would just be Andy's opinions that you should listen to probably. A cluster. So a cluster is a whole bunch of nodes, a node represented by a rectangle. So node 1, so this node is, think of it just like a desktop computer, but instead of standing on your desk, it's screwed into a rack. It has a motherboard, has a CPU or 2 or 3, it has a GPU maybe, it has some RAM modules, it has some hard drives, a networking interface. It's a computer in every sense of the term computer. And there's going to be many of these. And we tend to organize these things onto what's called a rack. So we'll have literally like a standing rack of a couple of metal bars with a whole bunch of holes in it. You just screw these things in, and then they talk to each other using some sort of networking interface. The thing in blue at the bottom is every rack usually has some sort of networking switch. Think like a router that you use at home for connecting to Wi-Fi. Basically that, although sometimes not using Ethernet, using some other types of communication interfaces. Then a supercomputer typically will have many, many such racks of nodes. So like Cedar has several hundreds of nodes, maybe even thousands of nodes. Each rack has its own networking device, its own switch. Nodes within a rack can communicate to each other very, very quickly. Nodes across racks are going to communicate with each other relatively slowly, high latency. And there's usually some relatively high latency but extremely high bandwidth connection between racks. The nodes may not necessarily be homogeneous. They're not all going to necessarily have the exact same computer or internals inside. Some nodes are going to have really huge amounts of RAM. Some are going to have 4 GPUs. Others will have no accelerators or GPUs at all. In Compute Canada, we usually have 3-ish categories of compute node, just a general CPU node that has lots of CPUs and a medium amount of RAM, a couple of extremely high RAM nodes, and then a couple of nodes, I say a couple, I mean like hundreds of high RAM nodes and hundreds of GPU nodes. And usually when you start to schedule jobs, you will request, I want this type of node, and you'll get one node that falls into that category. But we'll talk about that more in a moment. Last type of node that you might run into is usually called an infrastructure node or an infra node. These are usually one-off nodes that handle a very specific job. So one type of infra node is the login node. When I do SSH ANDNP at cedar.computecanada.ca, this is what I'm going to be interacting with, a login node. So I ping Compute Canada, it says you're going to go to login node 2, and then I end up with a terminal instance that is SSH'd into login node 2. Typically speaking, there is no direct access to compute nodes. There's no way to access those from the outside. There's a firewall in between those nodes and the internet, possibly no internet connectivity at all on those nodes, and you talk directly to the login node. Those login nodes talk to some special node that's also an infra node, and it actually will send jobs out to the compute nodes, and we'll talk about the purple node in a moment. Oh, a nice little animation. I didn't do that on purpose. So a couple of details about login nodes. This is where you tend to download your data sets. It's also where you tend to download and compile your software. I have a little numeral here. This is where you compile your software, assuming that your compilation doesn't take any longer than an hour-ish. It doesn't take too many CPUs. It doesn't take too much RAM. So as long as you're reasonably behaving, this is where you tend to compile your code. And this is also where you actually submit the jobs that are going to be run on the compute nodes. Compute nodes have no direct access from the outside world. You have to talk to a login node. That login node will talk to the compute nodes on your behalf. There are links that can be created once you have access to a compute node, but that's probably beside the point here. Typically speaking, most compute clusters do not give you internet access from the nodes. They're usually totally sandboxed, can't access them outside of a very strict firewall. Some of Compute Canada systems are a bit older and haven't actually adopted this standard, and so some Compute Canada systems, like Cedar, I believe, will give you internet access from a compute node, but you should typically try to structure your work assuming that that is not true. Otherwise, compute nodes are responsible for executing jobs and giving you access to GPUs or other accelerators, though for Compute Canada's sake, I think that's just GPUs. All right, the purple box. So the purple box is the scheduler. Sometimes one or more infra nodes are going to be dedicated to running this scheduler. Specifically, Compute Canada, all of the systems use Slurm, which is just a particular scheduler technology, if you will. The scheduler is responsible for running your jobs. So to make that explicit, you write a script, usually a bash script, like dothing.sh, really cleverly named, and that encodes your job. So dothing.sh is going to encode some requests for resources, is going to encode maybe some environment setup, instantiating your virtual environment or what have you, and then it's going to call like a Python script or a Julia script or whatever sort of script that actually executes your job, saves the data to disk somewhere, and then terminates, usually with some sort of like exit code. This worked, this didn't work. You tell Slurm to run that job by calling this command sbatch. It has a couple of command line arguments, probably not going to talk about the details here, but you call sbatch and you say, hey, run this script, and that's going to place a job in a queue, meaning it is not going to execute immediately, it's just going to return back and say, hey, I added this to the queue, good job. You can check the status of your queue using the sq command. At some later point in time, one of those compute nodes will become available. Nobody's running any jobs on it, or at least nobody's running any jobs on enough CPUs that you can actually fit your job. When that becomes available, Slurm will be responsible for clearing any sort of residual data. So maybe that was running some like secure private health processing scripts. You want to make sure that there's no cross job contamination. So Slurm will be responsible for making sure that all of the data from previous jobs is gone, it's cleared, nothing's in RAM, nothing's on local memory. Then it's going to set up an environment, a compute environment on that node for you. So that might be loading certain modules, that might be making sure your path variables are reasonably well set, and then it's going to execute your job. One really important thing is it will only execute jobs for a fixed amount of time. There's no way to say, run this until completion. That is not a concept that the scheduler has. Instead, you will say, run this for 6 hours or until it completes. So if it completes in 6 minutes and you ask for 6 hours, that's typically not a great thing because now it's way over allocated. Yeah, so run for a fixed amount of time. Slurm otherwise handles graceful completion, like your script returns an exit code of 0 and says everything worked great. It handles errors and will log these to some log file somewhere. It also handles canceling the job due to time limits. If you say, hey, run for 3 hours, and it's actually going to run for 6 hours, at 3 hours, 0 minutes, and 1 second, it's going to kill your job, and it's usually pretty strict and pretty harsh about killing the job right on the time limit. There's a little flexibility if there's not a lot of contention on the nodes. Slurm actually has the ability to let jobs run past their time limit, But it turns out in Compute Canada, people are requesting approximately 10 times the number of resources that we actually have ability to provide, meaning that there's always someone waiting in line, so your job is always killed right at the time limit, practically speaking. And to be clear what a job is, I'm throwing this word around, I've even highlighted it in orange. A job is a specific request for resources, like I want 4 CPUs, a little bit of RAM, and a GPU. It is the script that actually executes. A job generally can span across multiple nodes. By default, it will span across nodes. So if I ask for 4 CPUs, that might be 1 CPU over here, 2 over there, 1 over there. But you can request it not to span across nodes. The major trade-off here being it's often easier to find 1 CPU here, a couple over here, and 1 over here that are free, so that's going to schedule a bit faster. If I say I want 4 CPUs on that node, or on any node, that is going to be much harder to find. As I've mentioned several times now, but it's really important, so I'm just going to mention it again. Jobs are time limited, and you do have to provide an estimate of how long a job is going to run. And they're generally sandboxed, meaning that if you ask for 4 CPUs, you can write clever code to get access to more, then you get an angry email. Generally speaking, if you ask for 4 CPUs, Slurm is going to hand you 4 CPUs, and that's all you get access to. You can't go over your RAM limits that you've requested, you can't go over your CPU limits, you also can't accidentally access data that somebody else is using. Right, a couple of other comments about the scheduler, other things that it is responsible for. It handles fair share. Fair share is a metric that is used by Compute Canada, by Slurm actually, to make sure that every single account is using its fair share of resources. So specifically, accounts are usually owned by the PIs, and then we have sub-accounts that are attached to their account. So Martha has an account, the default account, def, white M being her username, and I have an account, ANDNPATT, that is a sub-account to def white M. So when I go to execute a job, I say use def white M, use Martha's default account, and I'm running as this user, as ANDNPATT. This is important because then when they charge my account for my amount of usage, that charge goes into Martha's account. So Martha's account has now used X number of CPUs, I have now used X number of CPUs, and Martha's account is the aggregate of all of her students. So then if I have run a whole bunch of jobs and then Khurram wants to go run a job on Martha's account, and Khurram hasn't run anything recently, I have used a huge amount of Martha's total account, her total allocation, so Khurram's jobs are going to float to the top. His will get scheduled before mine, generally speaking. This also handles fair share across accounts. Martha has an account, Mike has an account. If Martha's students are using way more than their fair share of compute at the moment, and Mike's students haven't used any compute at the moment, then Mike's students will typically get priority over Martha's students. So then the total priority is going to look like within a lab, if I've used the most, I'm going to have low priority. If my lab as a group has used the most, that lab as a group is going to have low priority. So if I am in a lab that has used a lot of compute and I have used a lot of compute, I'm going to be waiting a pretty long time before my jobs execute, trying to maintain some degree of fairness across everybody. This fair share is used to compute a priority level, specifically using that within and across count fair share metric that I was talking about, but also based on the length of the job. If you're requesting a fairly short job, then that's actually going to get a pretty major priority boost. If you're requesting a very long job, it's going to get a major lower priority decrement. What's the opposite of boost? Anyways, these are the buckets that your jobs are going to land in, that Slurm has, actually that Compute Canada has defined for Slurm. So anything less than 3 hours is going to get the largest priority boost, anything less than 12 hours, a slightly smaller priority boost, and so on. It's also based on the requested resources. So obviously if you're just asking for 1 CPU, a couple gigabytes of RAM, that thing's going to have massive priority, it's going to run instantly. If you're asking for hundreds of CPUs on lots of RAM, that might take a day or two. Priorities are based on your annual allocation. So every single year, the professor is going to have to request a renewal to their account. And then all of the usage from the past year is gone. That is in the past. We're not going to hold it against you. You now have a new allocation, and priority is going to be counted against that allocation. As I mentioned, people are requesting far more resources than Compute Canada can actually generally serve. Which means that this sort of fair share of trying to balance things, the idea is if I use 3 years worth of compute all at once, and then someone else wants to use a whole bunch of compute, that's going to sort of aggregate that, or that's going to average out over time. So I can take this really big spike. I don't have to use my entire compute allocation continuously at a low level. I can do it in this very spiky way. The problem here, though, is because there's not enough supply for the amount of demand, things don't actually tend to balance out perfectly. So you might actually end up, even if you are allocated X number of CPU years for the year, you may not actually get X number of CPU years for the year due to this over demand. Otherwise, you interact with the scheduler using 3 different commands. This is for submitting jobs to the scheduler. These are sbatch, srun, and salloc. Sbatch generally says, hey, just add this to the queue. I need this to be run at some point, hopefully in the near future, but I'm not specific about when, or I don't care about when. Salloc says, hey, try to schedule this as soon as possible. Still goes in the queue. You're not skipping the queue or anything like that, but it does go into a special queue that has extremely high priority for very small jobs. I think a limit of 4-ish CPUs, 8-ish CPUs, I don't remember now, 3 hours, small amount of RAM. And an srun only works within a job, once a job has started running, and says, hey, you have given me access to X number of CPUs, use one of those CPUs for me, please. And so then it runs instantly, but it still interacts with the scheduler because if things are scheduled across many different nodes and you say, hey, I want you to run on one CPU, you may not know what node you're not currently using within your job. srun does, so srun will go move your job over to the node that you are asking it to run on. So those are all the major terminology things. It also gives you a reasonable idea of what the scheduler is, I think. The other really important thing I want to talk about, and Khurram is actually going to talk about a bit more, is storage. The really hard part about a cluster is that when you interact with the cluster, you're going to see like a project disk. That project space has some amount of memory allocated to you, amount of hard drive allocated to you, but that thing is actually built of many hard disks, a couple of hard disks on every single node. And so all of these hard disks are going to have to communicate with each other and try to synchronize to make sure that you know what data is available and that data is spread reasonably across nodes to prevent failure and data loss and so on. This ends up with a fairly complicated looking thing that's all abstracted away and hidden to the end user so it looks to you like you're interacting with one single disk. This can be a little misleading because you're not interacting with one disk. This is radically different than our laptops, which generally have really fast solid state drives in them now, versus this thing that is an aggregate of many extraordinarily slow hard disks that are communicating over a network, which adds its own degree of latency. And so one of the problems that can occur is I was allocated this particular node on this rack to run my job, but my data exists on this hard drive on another node on another rack, which means that it's going to have to communicate to the switch on that rack, over to the switch on my rack, up to my node in order for that data to be moved, or to be accessed rather. Not that this is probably ever going to be important, but the file system that is used on Compute Canada is called Lustre. It is a distributed file system. It orchestrates all of that moving data around and making sure that copies of data are saved on multiple different hard drives. There is some tuning you can do based on your specific hard drive usage by interacting with the Lustre file system directly. Compute Canada does give you access to do that. But even in their docs, they say this is really temperamental. Probably don't touch the defaults unless you really know what you're doing. Otherwise, this file system is going to communicate over a networking interface, which means it's very high latency, and there's typically going to be lots of network contention. Lots of people are trying to access files. They're going to have one node here, files over there. You're going to have a node here, files over there, and all of these things are trying to cross-communicate. It's very high latency, very noisy, and tends to take a lot of time. And as a result, it tends to be pretty heavily policed. They try to make sure Compute Canada monitors all of your file usage and tries to make sure you're not opening lots of file handles. You're not trying to access files frequently because that places a huge amount of contention on the file system. We frequently will see in our Compute Canada Slack channel, like, hey, is anyone having issues trying to type in ls right now? I think that was the most recent message in the channel, in fact. And the answer is almost always yes, everyone is having issues accessing files at the moment because there are always issues. But a couple of caveats here. It does implement a tiered storage. So if I'm on this node and I've requested data that's all the way over here, that data, once I've requested it, will get moved to my node, usually, maybe within 1 or 2 accesses to the same data. That way now the data is co-located with the code that's running it, which means this is also true of the login nodes, which also means if I'm on a login node and I'm trying to compile, it will be very slow at first, and maybe it'll speed up with time as more of my data actually gets transitioned over to my node. So that's node to node tiering. There's also within node tiering. If I continue accessing that data many times, it'll get transitioned from a hard disk to a solid state drive and become even just a little bit faster. Of course, this is only helpful if you're being relatively constrained to a single node. I mentioned that things are going to get spread out over many nodes, which then means either the data is going to get cached on all of your nodes, or it means you're just inevitably out of luck and everything is always going to be relatively slow when accessing the hard disk. This is actually pretty important with things like Python, where all of your files are very small, and there's usually many, many, many of them somewhere inside your like virtual environment or wherever you've installed all of your libraries. And so instantiating Python and loading PyTorch, for instance, which seems to be particularly bad at this, can take a pretty long time the very first time, because PyTorch is made up of a ton of incredibly small files, and so it can take a very long time to import at first, as an example. Nodes also have local-only storage, something that once I've created a job and the job is running on a node, I can now access a solid-state drive, a very fast solid-state drive that is local to that node. It's extremely fast. As soon as my job ends, that is completely cleaned. In fact, they write zeros everywhere to it to make sure that you can't have any sort of cross-job pollution or contamination. And so if you need really fast storage on your compute node, for instance, installing a virtual environment locally to your compute node before actually trying to execute your Python code, that can actually speed up jobs quite a bit. Mike?
For compute nodes that don't have outside internet access, how do you install software on your virtual machine, on your virtual environment?
Yeah, so
Can you repeat the question?
yes, so what if my compute node does not have internet access? Then how am I supposed to install software on the local hard drive or data sets on the local hard drive? You can actually create an SSH tunnel and tunnel through the login nodes in order to get to the internet in a secure way, and that will give you one option. Another option that Compute Canada recommends for specifically installing virtual environments is that I install the virtual environment in Scratch or in Project. I zip it so there's one single file, and then I transfer that file to my local node and then unzip it there, and then everything's set up. That way I don't actually have to reach out to the internet. And because that's just one file, that is much easier for the caching system to make use of. Good question. All right, I think the last thing I wanted to talk about before I get into my opinionated device is software. Software is handled using LMod, which is a module loading system. So Compute Canada has a whole bunch of software already pre-installed. It usually maintains several versions of the software, many versions of Python, for instance. You use LMod to actually load that software in. One important thing is it is compiled specifically for the architecture for the compute node, so it's relatively fast, typically. They also maintain a wheel library. Wheels are pre-compiled Python binaries of libraries, so they have a whole bunch of Python binaries. Most of the most popular used Python binaries stored in a library that have been locally compiled for that compute node. So when you do pip install, you're actually first going to reach out to that cache that is automatically configured for you. You'll try to get a pre-compiled wheel. Otherwise, you'll reach out to PyPy and ask for its pre-compiled wheel. Typically, the pre-compiled wheels are much faster than PyPy's versions because they take advantage of the local compute node, the actual architecture of the local compute node. They're also typically extraordinarily out of date and slow to update, so trade-off. And here are the two commands. I don't know why I felt the need to share these since I didn't have any other commands on the slide. All right, last couple of things. Piece of advice, test your stuff. Make sure it works before you run, because if it doesn't work successfully and you ask for a whole bunch of compute power, your account gets charged for all of the compute that you've requested, not necessarily the amount that you've actually used. We've tested this empirically by accident many times, and it turns out it can be a rather expensive mistake. And so I tend to personally follow a pretty strict sort of pipeline. I start by testing the software itself. So I've written a Python script, and I test exactly that script by asking for an interactive job and running the script and making sure it doesn't explode. I usually catch 99% of my bugs there. But I also need to make sure I test my scheduling script, which has its own set of logic, like setting up my virtual environment, actually calling things, making sure I handle when it's time for the job to end, and so on. And so I'll schedule a very small job, ask for a very tiny number of resources, just run a couple of instances of my code, of my library, and make sure everything works. And I pay really close attention to how long it takes to run. For this script, I usually request 2 or 3 times the amount of run time that I actually think I'm going to require, so that I can get an accurate estimate of how long it's going to take. Since I'm only requesting a handful of CPUs, that's a pretty minimal cost. And then if I'm running a really huge study that's going to access a ton of resources, if it's possible, I try to do it in small batches. That way I can fail early. If my statistics aren't panning out, if my experiment is not panning out, maybe I'm going to quit early. If I catch that there is a bug that is gnarly and hidden, and like I'm saving my data in kind of a weird way, which I didn't detect with all my previous testing, this is another chance for me to quit early. and use checkpoints, just in case anything starts to run for a while, and for some reason you estimated the amount of time, but it's still taking longer. This way you don't accidentally burn a whole bunch of compute, save absolutely nothing about the state, and then have all that compute be completely wasted. So checkpoints are typically very important. I tend to prefer using the locally installed software whenever possible. You can even reach out to Compute Canada to ask them to install software or update a version. They're pretty responsive about it, though usually they're very quick to say, no, sorry, we're not going to do that. But they're at least responsive, so you'll know they're not going to do it pretty quickly, which is nice. And the last couple of pieces of advice are all be kind. Be kind to the scheduler. If you're scheduling many jobs in quick succession, keep in mind the scheduler is this prioritized heap. And the fastest algorithm for managing a prioritized heap is log n being the number of things that are currently in the heap. If you're scheduling m jobs, then the fastest way I can schedule them is m log n. It tends to take a decent amount of time, and tons of people are doing this. That can be a pretty high latency. So be kind to the scheduler. Give just a little bit of time between each job. In my Python script, I just tell it to sleep for 2 seconds and then schedule again. Be kind to the storage system. Lots of people are using the storage. Really small files, actually file handles cost a lot. And so if all of your files are very small, you're going to have lots of file handles because you have many different files. And that tends to be very costly to the storage system, and that impacts everyone. If one single person is being unkind, everything is fine. If everyone's being unkind, not so good. Be kind to your group, but don't be afraid to use the resources either. So make sure you're actually balancing your group usage a little bit. Make sure that you're not using all of the compute in your group. And most importantly, this shouldn't even be your decision. Talk to your advisor and just communicate with them. I'm going to use X% of the budget to run this experiment. Is that good with you? Is this how you want to spend your resources? Now, a lot of my experiments tend to be like 0.001% of the annual budget. If I pinged Martha every single time I'm going to use 0.001% of the budget, she's going to just block me on Slack probably. I'm not sure. Actually, Martha's so nice, she would probably answer all of them, and that would make me feel worse, honestly. And in general, if there's any doubts, we have a Slack channel called Compute Canada in the Amii workspace. Definitely ping there. We're generally pretty quick to respond. There's tons of students with knowledge about these things that are going to respond or at least commiserate with you like, yep, it sucks for me too. And at least that'll make you feel a bit better. You can also reach out to Compute Canada support. Like I said, they're actually really quick to respond to most things. They can be extremely helpful when it comes to not wasting their compute resources. So they'll be very motivated to help you not waste resources and tend to actually help you design job scripts. They'll help you write code and so on. I think that's everything. I see another question, Mike.
I just want to say this about Compute Canada. They really want you to use their resources. They live off of you using their resources. If they only get 50% usage, they can't go to the government and say, we need more resources. So if you're not using the resources, then they don't get more resources and we have fewer resources. So don't be afraid to use the resources. That's the number one thing. The more we're using it, the more we get.
I think I saw another question to my right, but maybe that was just seeing movement. Yeah. Yeah, so the comment is we should make sure we cite them if we use their resources. Yep, that's probably almost certainly true. I believe in most papers you should have an acknowledgement section that says, I acknowledge that I used X resources from, yep, I totally agree. I wonder how many times I haven't done that. Any other questions? Yes?
When we're allocating some time to run the job, but it completed before that, there is no way to actually say, oh, I don't want this allocation anymore. Just when it completes, stop.
So the nice thing is when it does complete, it will stop and will backfill. It's called backfilling. It'll let someone else start using the node, but it will still charge you for the full amount that you have requested. And that is actually a configuration. We've talked to Compute Canada about this in the past. Slurm doesn't have to do that. And we've gotten mostly non-response, no comment kind of responses as a result. So yeah, I see Fatima in the back.
If I have 1,000 tasks for a huge study, is it better to partition it into 10 or 100 small batch jobs or just one batch job? That's I didn't understand that.
Yeah. So what I meant by this was referring mostly to jobs themselves as opposed to necessarily like tasks within a job. But the basic idea is exactly as you said. If I'm running a huge study, it usually means like multiple environments, algorithms, hyperparameters, seeds, whatever. We have some cross product of things that ends up with a lot of very parallel or parallelizable tasks that I could run. So my general advice is just to break those into chunks, whether that's within a job or across jobs is not super important. Just like run 10% of your runs. If I'm going to run for 10 runs, run the first run and then make sure everything worked really well. If I'm going to run for 10 runs, then run the second run, make sure things work well, check your analysis scripts to make sure statistics look the way you kind of expect them to, and there's nothing too crazy going on. That way you can just stop early in case things are not working as expected. Yeah.
Is there some optimal chunk of submit time? Like if I had if the minimal amount of parallelizable thing is 1 minute, it probably doesn't make sense to submit 100,000 1-minute jobs. Probably doesn't make any sense to submit one 100,000 minute job. I do know there's a limit. If you're under something, the scheduler puts you in a different bucket.
Yeah.
Maybe you said that before I walked in because I walked in a little late.
I did. Oh boy, I have so many. This is so much more work than I thought it was going to be when I started. Yes, there are buckets. There are 3 hours, 12 hours, 1 day, 3 days, 7 day, and 28 days. And the important thing is these buckets are actually nodes. These are allocated nodes. So they have set aside, these nodes are only going to run jobs less than 3 days. These nodes are only going to run jobs less than 12 days. So if you're in that 3-hour bucket, or sorry, hours, not days. If you're in that 3-hour bucket, you get access to every single node on the machine, which generally means you're going to be able to schedule a lot faster. So typically, yeah, the ideal time is to batch things up in serial so that they take 3-ish hours, maybe just a bit south of that, just to make sure you have a little wiggle room, and then have many 3-hour jobs scheduled in parallel. Yeah, I think Fatima and Ezra, go Ezra first, since that's where the mic's headed.
Is there a point at which if you would have too many 3-hour jobs? Like, is there a max? I think there was, maybe?
I can't remember the max off the top of my head. It's either 1,000 or 2,000 jobs that you can have in the queue at any given point in time. I want to say it's 2,000 jobs you can have in the queue at any given point in time. After that, then, yeah, trying to make those 12-hour jobs, for instance, might be optimal. Or even just submitting 2,000 jobs, letting those run, submit the next 2,000 jobs, letting those run. It's up to you how much you want to really interact with the machine, how much your time costs.
You hear me? Yeah, okay. So yeah, you did you say something about what is the minimum length again? Like, so 3 hours is good, but like to Mike's question, if I have 1,000, if I can run 1,000 jobs in a minute, I would prefer that over
Waiting
letting
3
it go
hours.
for 3 hours, right?
Yeah.
So is there a best practice as to, maybe at least have jobs which are 10 minutes long or an hour long or something?
Yeah, the documents, so no, the answer is no. There is no actual hard enforced limit. The documentation for Compute Canada does set some, we prefer you try to reach these limits. And I want to say it was 30 minutes or an hour was we prefer you keep your jobs about 30 minutes or an hour. I'm mostly making that up. I would have to go look at the document again to see what they suggest. It's 30 minutes, okay. Khurram agrees 30 minutes is the recommended minimum. Yeah, Hassan.
A bit of a low-level question. Is 3 hours only for SLOC, or can we submit SBatch with 3 hours and get benefit?
Yep, you can. It is for the overall queue, so SBatch is queue. And SALIC is slightly special in that if you request 3 hours and some number of CPUs, you get in an even more special queue that is reserved exclusively for SALIC jobs, the interactive queue. Yep.
If there is no internet access for a node, how can I use, for example, WAN-DB to online log the outputs?
Yeah, that's a really good question, and I will answer the question and then I'll give an opinion. So the answer to the question is you can use an SSH tunnel. Basically, you SSH into the login node, which does have compute access, and you pipe your internet access, or you pipe your network traffic through that tunnel, so that then reaches out to the internet from the login node. Now that tends to be fairly high latency, but for something like a database where you're just pumping data outwards and not doing any sort of back and forth communication, that latency isn't too big of a deal. My personal opinion is I don't tend to use such things because they're fairly difficult to manage and set up. I'm a little lazy. I'd actually just prefer write my own system that does everything locally. And I'm also slightly distrustful of when the internet goes out and then my job is still running and I no longer have any sort of access. And that does happen a non-trivial number of times, or at least enough for me to be a little cautious. So that was the answer to your question, and my opinionated answer, take with a grain of salt. Fatima.
So, do you have any, I guess, for example, I ran a job in Salok, and it ran fine. And I had some unit tests. It was like a mini version of my actual experiment. And then I deployed it in SBatch, and I see that it failed. So, I just don't understand, why would that happen if you're, how do you go about, debugging that or figuring it out?
Yeah, how to debug is often very challenging for these kinds of things. So when something works in salloc but doesn't work in SBatch, the first place I might look is salloc will SSH you into a shell environment. And so it's setting up a whole bunch of things implicitly. You have logged into this node. If you're using like bash, for instance, it has executed your bash init.rc script. Any sort of other environment variables that you might have set up is going to go ahead and set up for you. SQ is not necessarily going to set up the exact same environment when it runs something on a compute node. So for instance, if you have locally run module load Python 3.11, and then you do salloc, it's still going to have Python 3.11 loaded. But if that's not your default module, then when you do SBatch, it's going to load Python 3.9, for instance, if that was the default. And so that would be the first place I would tend to look for these things. As to how you actually debug that intentionally without guess and check is mostly, there's not a good answer to that. Yeah. Seeing no more questions, I think I'm going to pass it off to Khurram is going next. I believe, yes, I'm going to pass off to Khurram.
So hello, everyone. My presentation is very short. It's just about one topic, which is how do you scale experiments in a way that you can have hundreds or thousands of parallel jobs. They're all writing, and it still works fine. So a very common workflow when you're using Compute Canada is that you write and debug your experiments on your local machine first. Then you're going to set up the environment in clusters and run a small instance of that code, like Andy was talking about, that you run it. It all works fine. So you maybe ran like 10 instances of your experiment. It was all good. Then finally, you schedule a very large array job. So an array job in Compute Canada is just a job which you ask for the same resources but multiple times. So maybe you ask for 1,000 CPUs, and every CPU is going to run one instance of your job. So first part was good. It works on Compute Canada when you run a ton of them, 10 instances of them. Then you're going to run 1,000 of them, and then it's not going to work. And some problems are going to be about, as Andy was talking about, storage. So what you can expect is that if you're not taking into account some important factors, your jobs are going to take much longer when you run them on 1,000 nodes as opposed to 10 nodes. And the cluster might become unresponsive, and this time it would be becoming unresponsive because of you. And worst case, you might get a strongly worded email from the Compute Canada admins, which happens more often than you think. Hasn't happened to me, but it happens. Okay, so how can you run large-scale experiments and not run into these issues? So I'm going to propose 3 solutions in terms of how some are easy to set up, but they're not very nice in my opinion. Some are a bit hard to set up, but they give you a lot of benefits in terms of ease of use. So let's look at the 3 solutions. So one solution is that, so the important thing is that now that you're running things on the cluster, you cannot treat the storage the same way as you treat your laptop storage because it's distributed and it's over the network. So one thing you can do is you can keep all your data in the RAM as your program is running. So you ran a program, it's going to log maybe your error or a bunch of other things. You can keep all of this in RAM, which means you keep it maybe in a Python list or in a Python object or whatever language you're using. And then once you have accumulated all this data and your program has finished, you serialize it, and you dump it in this Scratch directory. And Compute Canada does recommend to use Scratch and not project or home for this. So just dump it in the Scratch directory in a few files, not in 1,000 files. So ideally, maybe you can write one large file at the end of your experiment, which contains all of your logs. And then you copy that data from your Scratch to your local machine for processing or plotting. And that would be probably the first way most people set up their experiments in the beginning, because it's very easy to do. The second thing you can do is, you can use this special fast local storage that is available on your local machine. So it's called Slurm Temp dir. It's basically an SSD, and you can write to that local SSD just like you would to your local machine. Now, if you're doing this, then you don't have to modify your code. If your code runs fine on your laptop, it'll run fine on the Compute Canada, as long as you're writing to this specific storage. And then you can archive all the logs in this storage into a single file, and then copy all of that to Scratch before the job ends. Now, this part is important because, as Andy mentioned, as soon as your job ends, this local storage is going to disappear. You only have it for as long as you have access to that job. So you have to archive it, copy it to Scratch within your SPAT script. And then this third method that I use, which Andy just said he doesn't like, that's his strong opinion, is to transmit data over the network to your own personal external storage. So just bypass the storage units on Compute Canada. And what that looks like is, well, you can transmit all the data to an external database, and there are many examples. There's OneDB, like someone asked, but you can also have a MySQL server or PostgreSQL server. And you can, if you don't want to use OneDB, if you want to use your own servers, you can get VMs from the Alliance or Compute Canada for hosting those databases. So your PI has to send a request, and then they have a lot of them available. And when I talked to them, they said that no one uses them. They're all available, so it should be pretty easy to get a good VM for hosting your database. These are three methods. They make different trade-offs, so I just want to talk about the trade-offs. So the first method is very easy to set up. You're basically storing all the data. You're going to serialize it. You're going to dump it. So everything can happen inside your code. Super easy. The problem that the reason I don't like it is your data is not available in real time. So your experiment has to finish all the way before you can start seeing the data. And being able to see the data in real time can be extremely beneficial for some experiments. And the third is that it's also not easy to plot with that data. Like, it's a single file, it's serialized, and you're going to copy it, you're going to open it and maybe Python, then load it, then deserialize it. It's a bit of a mess. If you look at the second method, ease of setup, again, very easy. All you have to do is to log data on a specific storage unit. It's again not available until your job finishes, so that's not great. I'm going to say it's a little bit better in terms of plotting, because you can actually just directly plot things in that local storage unit. So you don't have to write a single file. You can create 2,000 files as your experiment is running. Then you archive them, copy them to Scratch, copy them to local storage, to your local machine. But you can do all the plottings as your code is running. So you don't have to serialize it into some format. You can do a bunch of the stuff as the program is running. So it's pretty good. The only downside of that is that you just have to remember to copy it. If you don't do that, you'll lose the data. And let's look at the third one, ease of setup. I'm going to say 1 out of 5. It's very hard to set up. It's not very hard to set up. It's a bit annoying to set up because as you don't have internet access on most of those, so you would have to set up the tunnel that Andy was talking about. But that tunnel is not that hard to set up. Like, there is a one command, we can share it, you can add it on your SPAT script, and that's it. So your tunnel would always be ready whenever you run your script. And based on my experience, it works really reliably. So I have probably done maybe like 200,000 experiments over the last 2 weeks. And if I check like all of them, like how many of them were finished, I think maybe I lost 1 or 2 jobs in the ether of the whole process, or everything else was logged and everything else was perfectly fine. Your data is available in real time, so you can literally see the plots as your experiment is running, which can help you sometimes end experiments earlier because you can see that, oh, maybe this is not the right experiment setup, or do you want to change things as you're running. And then one really nice thing I like about this is that I can start, so if I'm running, let's say, experiment for 30 seeds, I can start plotting results for like 2 seeds as it's happening. And then I can get some confidence that if it's even worth running this for full 30 seeds, or if I can just cut it short. And then ease of plotting is if your data is structured, it's in the database. If you know how to use databases, it's going to be very, very easy to plot things. And then I have one example of like my system that's running. So this is logging data to a SQL database. The experiments are running on 700 CPUs. They're across the 3 clusters. Some CPUs are on Narwhal, some are Beluga, some are Cedar. They're all logging to the same database, and they're logging a lot of data. So they're like, at this point, you see that there are 750 queries per second, and a small database with 4 CPUs can handle this perfectly fine. So it scales very nicely. And then I've also run experiments where they were running 2,000 experiments simultaneously, and it worked perfectly fine. So if you are interested in those kind of large-scale experiments, I think this is worth setting up. And that's about it. I'm not going to go into details, but if you're interested in setting one of these up, you can always ask me or other people. Yep.
So these VMs, are they restricted to just MySQL, or can you even run with?
It's like a normal VM, so you can run whatever you want on it.
All right, thanks.
This, I'm not using that VM. I'm using like a Google Cloud because they also give you credits. But yeah, you can use those.
Okay, thank you.
How does the VM compare to managing your own database within your job?
So when you say managing your own database, I guess you're saying like a file-based database?
Yeah.
So if you use like SQLite, which is, you don't need a VM, you can just run it on the file system. If you are storing it in like Scratch or one of those, it's a terrible idea. It's not going to work really well. And then also those have a hard limit of, I think, 40 concurrent writers. As soon as more than 40 processes try to write to it simultaneously, one of them will just block. So that was my first strategy. I tried SQLite, did not work, and then I had to like, okay, I'll just do the full thing. Okay, there are no more questions. We can go to Shubham.
Hey everyone. So my talk is going to be about a problem I guess a lot of us have faced while running Compute Canada, and that is often we don't find the dependencies that we need, and then we contact Compute Canada support, and they'll get back to us in a few days, say that, okay, we cannot really compile this for the Compute Canada system, and then we are left with no choice but to think of some other experiment. So this talk is going to be about running containers in Compute Canada, which gives you a way to get past these issues. So a few weeks back, I was trying to install this simple Python package, which using just regular pip install memory maze, and then here I have an issue. And when I tried to look into, try to search for this issue, I had no clue what was going on. Because this issue only occurs in Compute Canada, and no one outside who knows anything other than Compute Canada knows about these kind of issues. So ultimately, I figured out that to fix these issues, I need a specific version of the Mujoku library, and for that, I need sudo access to compile that library. So ultimately, I'm left with frustration, and this is not what I did, but yeah, this is what was going on in my head. So what are the problems this occurs? One of the problems is we do not really have sudo access. Compute Canada cannot give us sudo access for a variety of reasons, which they would not describe, but I kind of get the point that if a lot of people have sudo access, they're going to change the system in a way that might make it unstable for every one of us. Which means we do not really have a way to run apt-get or yum install if you're using a different Linux version. You cannot also install specific drivers, which you might need for specific softwares. And this makes compiling difficult. Often other people's code depend on specific versions of drivers or dependencies, and compiling these would require you to have sudo access so that you can install certain packages. And yes, getting resolution from the support team, even though they are responsive, it takes time because they are also people. They have to actually go and try to install these things. And it's often a tedious process, and often it does not play out really well, and you do not really get to use the exact version that you want. So the solution to all of these problems is often virtualization. And virtualization is basically a way to run virtual machines inside Compute Canada. So what do I mean by that? It basically means you can run an entire Linux system inside of Compute Canada without interfering with Compute Canada's stack. So each virtual machine will operate independently. That means that whatever is happening inside the virtual machine stays inside the virtual machine. It's almost like you're running a Linux machine inside Compute Canada, and it does not interact with the Linux machine which Compute Canada might be running on. So the processes are completely independent, and they are shielded from one another. And if you want to do sudo, no problem with that, because virtualization basically gives you a way to work as if you are actually using that system, even though you not really have sudo access in the real Compute Canada, but inside of the container, you can have sudo access. So virtualization in Compute Canada is implemented through something called Apptainer, which was previously known as Singularity. In fact, they changed the name just around a month back, I guess. And the way they describe Apptrainer is, so this is the description of Apptrainer from the original website of Apptrainer. And it says that it is a container system for secure high-performance computing. What this basically means is that it's specifically designed for high-performance computing systems such as Compute Canada, and it is a way to run Docker containers inside Compute Canada. So how does this work? I'm going to give a short tutorial on how we can go about getting this set up. I'm also going to share the instructions of all of these instructions with you guys. So the first thing that we need to do virtualization in Compute Canada is finding a base image. What do I mean by a base image? A base image is like a Linux distribution. Let's say I want to run a specific software which requires a specific version of Linux, and it needs a certain CUDA version or specific set of softwares pre-installed. What I can do is, there's this website called Docker Hub, which has a variety of maintainers always pushing new images with different dependencies. What I can do is I can just browse this website and find out the specific image that I need. Let's say I want Ubuntu with CUDA version 11.7 installed. I can find that. And then what I need to do is I need to find the specific tag that image has. So for example, I'm looking here at Ubuntu version 23.04. So I can say that I want to pull this specific image. I want to start off my container with this specific image. The next thing that you do inside Compute Canada is you use this tag to pull this image inside your cluster. And the way to do that is first you load the module called Apptainer. This module allows you to run containers. So you just run module load Apptainer to do that. And the next thing you do is you say that you want to build an image by using a specific image as a source image from the Docker website. For instance, over here, I have an URL that says, I'm loading the Ubuntu 2004 image, which has CUDA 11.8 installed with CUDN 8 from the NVIDIA Docker container website, so Docker registry. And what I'm going to do is, I'm saying that I'm going to create an image called Ubuntu 2004 by using that as my base image. And I'm also setting some flags. I'm saying fake root. What fake root does is it gives me sudo access. So it gives you a way to fake sudo access inside this container. And then I'm saying that it's a sandbox image. What I mean by sandbox image, what we mean by sandbox image here is that we will allow changes to be made to the image that we are building now. So what this will basically do is it is going to pull the image from the Docker registry, and we will have a folder Ubuntu 2004, like you can see in the compute cluster. And this folder will have the image that I just pulled. It's going to have a bunch of subdirectories. It's going to almost have like a complete Linux system inside of that folder. So now I can basically shell into the folder like I would shell into Compute Canada. So I log into my Compute Canada, and then I can run a bunch of commands to shell inside the specific container that I just downloaded. To do that, what I do is I run apptainer shell, and again I say fake root to say that I want to be able to access sudo from inside. And then I also give another flag, which is writable. That allows me to make changes inside the container. And these changes will be permanent. So if you make some changes, you'll have those dependencies. You don't have to redo those changes every time you run your job. So with that, I am now inside the container. When you run this command, you will be inside a specific shell, subshell inside of your Compute Canada shell. And here you can basically run any sudo command that you want. You can now run apt-get, and it's almost like even though you are running it inside Compute Canada, it's not really interacting with the Compute Canada subsystem anymore. All the changes are happening inside the file. There are few things which are you need to fix. One of them is I was not able to, by just downloading the image from the internet, I'm not able to install commands using pip. And to do that, there's a short fix. All you need to do is you need to link a certain certificate from a certain location to a different location. And you can do that with the lns command. And with that, you should be able to install any pip packages inside the container system. Now, the last step that is remaining is to run commands inside. So what we did so far is we created a container that has our specific dependencies installed. Now we want to use sbatch to run specific commands inside that container. So when we are running sbatch, so one thing to keep in mind is we won't really be able to access sbatch inside the container. Because inside container, you don't really have the Compute Canada software stack anymore. It's a completely different virtualization, virtual subsystem. So to run commands inside Compute Canada, one of the easy way I have figured out is to set up something called an alias. So what I would do is, this is my way of doing things, but you can choose other ways of running jobs inside Compute Canada, jobs inside the container. But what I would usually do is I would add an alias inside my bash RC, and that alias would say that I would call that alias Ubuntu, and I will set it in a manner that it would basically run a command on my container. So what I'm saying here is I'm calling apptainer exec. I have a flag called nv. This nv flag is supposed to link the GPU if I want to access GPU. So this flag is very important if I want to access GPU inside the container. And then I'm going to do, I have a bunch of -b commands. What these are saying is that I want to bind my specific directories in Compute Canada inside my container. For example, if you just directly SSH into the container, you wouldn't be able to access all the specific directories like the home, the scratch inside Compute Canada. So for that, what you need to do is you can just bind all of these directories. And I have, what I'm doing essentially is specifying the directories that I want to bind and the locations inside the container I want to bind into. So every script that you run inside the container should try to access those directories instead of the actual absolute directories that you would have inside Compute Canada. So once I set up this alias, I have now a very easy way of running applications. What I can just do is I can type Ubuntu, because I have set up an alias called Ubuntu. I can just type Ubuntu, and then I can type the specific command that I want to run inside of the container. So I can say, for instance, in my Compute Canada, I had Python 3.9 installed, but if I type Ubuntu Python 3, it's going to show Python 3.8 because this Python version is now inside. When I'm adding the alias Ubuntu, it's now running it inside the container. So this is great. So this gives us a way to run the specific dependencies. We can install whatever we want. We can also, I've tried installing most of the stuff which I needed, and I haven't yet faced any issues. Maybe there are some specific drivers which will not work this way, but it has been working very well so far. There might be some issues of doing this. One is it might be slow for some workloads, because essentially what you're trying to do here is virtualization, and virtualization means there's a cost of converting from one specific way of doing one specific hardware compiled code to another hardware compiled code, and then this back and forth communication might have some cost. So, but I haven't yet seen any of that practically for the workloads that I have been doing. But like the most advisable thing to, like if Compute Canada gives you a solution to the issues, it's more advisable to use Compute Canada software stack rather than relying on containers. But often this is very useful if you're not able to find certain things inside from the Compute Canada support. The Compute Canada support is not able to help you in certain ways. Yeah, thank you.
I was actually playing around with the slowness a bit. And I wanted to just say one thing for everyone to know, that containerization is not virtualization. They're two different things. Virtualization really does emulate like the CPU. Containerization is more like, I have like a second disk that's running the same OS, and you have to run the same OS. That's the reason we can do Ubuntu. You couldn't use containers to install Windows. But with that said, the real problem comes down to, I think, what Andy said, that the wheels and all the pip packages are compiled for the node on Compute Canada. When you do it yourself, you're not getting it freshly compiled for your node. I played around with NumPy just as trying things out, just ran random, like, I'll compute some matrices and run some means on them. And I saw about a 10% slowdown. If I was just running straight Python code that wasn't doing anything that dropped down into C, then so that I wasn't experiencing its compiled, like its specialized compilation, I saw 0 slowdown. So I'm sure there's other areas where you could see more where the specialization for your hardware matters, but that's what I saw, about 10% for NumPy.
Yeah, it might also be possible that inside of the container, we can compile a lot of these binaries, like NumPy, and then maybe we would get the speedups that we would get.
Yeah, there's actually, there is a way, so I've also been screwing around with the slowness issue, trying to figure out what's going on. There is a way you can tell the pip inside of your container to reach out to that wheel library that Compute Canada has and prefer that if those wheels are available. Doing that, I still saw about a 3-ish% slowdown, which for a lot of workflows is small enough to not, that you can brush that under the rug. That's not a big deal. It is a little bit of work to set up. It was a little challenging because then I had Compute Canada was offering some binaries of one version. My container had binaries of another version. Some things were a little goofy to get synchronized. At that point, I spent more time making my container work than my original just raw installation. But of course, if you're deciding between, I literally can't run this because Compute Canada doesn't have the software and I'm going to have to put some work into the container, you should probably prefer the container or redesign your experiment or something if that's possible, but that isn't always possible. So yeah.
If there are people here who have done all of this hard work, is it possible that if just someone says, oh, I want to run Mujoko with PyTorch, install one thing where somebody has done the hard work of figuring all of these things out. You just install that thing and you can just start running off the ground. Is that even possible? Or?
Yeah, that is definitely possible. So that is one of the advantages of using a container system, which is you can compile these. So right now, in the example that I showed, I was creating the image as a sandbox image, but you can compile it as something called an SIF file. And that SIF file is basically just a single file which you can share with anybody, and it would have all the dependencies that you need. Yeah, so that's the way to use, you can have all the. Yes, so yeah, you could also have a Docker hub. So Docker has this Docker hub where you host these images. So it's also possible to have something called a Singularity hub. You can host these Singularity hubs as a lab. And then students can just upload images there and people can just pull images from there.
So was this within the job, or is this like something you get your job and you get your nodes and then you run this on the node?
So all of this right now I'm running not inside a job. It's in the login node.
Oh, this is all in the login.
Yes.
Okay.
So everything is running in the login node, except when you issue commands inside into the container. So you create the container, you install the dependencies from inside the login node, because you might not have internet access in a lot of the other login nodes, like Beluga and stuff. So you create your containers. Once you have all the dependencies, you test things, and then you can issue commands using some sort of a workflow like this.
Okay, so you then like request the job, and when the job runs within the jobs node, you access this container and run your things.
Exactly.
There. Okay. And if you have multiple nodes, then this container has access to all of those nodes' resources.
So it depends on where you store the container. So you can store the container in a Scratch. It might have faster access from there. Or if you in your script, you copy the container from your the current login node to the project node to your wherever the job is running, then it will probably be faster. So you can have a script to speed those things up.
Yeah.
But until now, I haven't really noticed any any slowdowns with that, because I'm running like hundreds of jobs where the container is just placed in my project directory, and it works fine.
Okay.
So
yes.
far.
I mean, so like if like the job itself requests 2 nodes, for example, simultaneously.
Yeah, that should be
same
fine.
script, and then both 2 nodes resources are available to that container.
Yeah, it should be available.
You said something, Hassan, that you then agreed with that I felt was not quite right. It's not that the 2 nodes are available in the container. Each node starts up the container, does whatever process. If the 2 nodes need to talk to each other, that can still happen. But it's not that the nodes are in the container. In fact, no. The node job runs, it opens the container and executes something inside the container.
Yeah, it's independent.
Yeah,
independently
so each running
of the
compute node
containers.
will be running its own container image. Now, they might share file systems that allow them to talk to each other, but they'll be running separately. Just as if, I mean, there's no different than if the compute nodes were running natively without running the containerization at all. The thing I wanted to mention is the SIF files. Given what Andy said about how files access, your container in sandbox mode will be many, many small files, as the way a normal Linux file system will look like. Yeah. You should probably, after you have your software on it, turn it into an SIF file. That makes it one file, and it now interacts nicely with the Lustre file system.
That is extremely important, yes, because not a lot of clusters will allow you to have a large number of files. Especially Skeeter has a lot of restrictions on the number of files you can have.
Is there a way to streamline the apptainer image creation, just like a Docker file would do for Docker? Or do we rely on shell scripts?
There is a way. So you can write something called, I guess, a singularity file or something. Basically, it's similar to the way you write a Docker file, where you can specify the base image you want to build and the bunch of instructions that you want to run after building off from that base image. And you can basically compile that Docker file instead every time you need your dependencies.
When you're going to submit a batch job, like in your scheduler script, then you need to have a line that says like load this container, like, yeah.
So the way I do it currently is my sbatch will invoke this command. So I'll have Ubuntu, then Python 3. So my Ubuntu alias is telling me that I want everything to run inside the container because it has the exec command in the alias. So what I will do essentially is I'll say Ubuntu, Python 3, and then the script name. So if I have a batch job, which has a lot of slurm IDs, then those slurm IDs get passed into the script so that I know which specific hyperparameter configuration I'm running. Is there any questions? Okay. Right. Thank you.